If x plus 1 over x equals 3, what is x to the fourth power plus 1 over x to the fourth power? Or the fifth power? Or the seventh? And if you can solve those, what about the 99th power? Most students try to solve for x. They get an ugly square root, and then they give up because raising that number to huge powers feels impossible. But you don't even need to find x, and you definitely don't need the binomial theorem. In the next minute, you'll get the exact answer using only addition, subtraction, and multiplication. Once you see the pattern, you can work out x to the n plus 1 over x to the n for pretty much any exponent you like. First, let's establish our definitions. P sub n equals x to the n plus 1 over x to the n. And we already know our starting point P sub 1 is 3. To build anything, you need two base values. So let's find P sub 2. Watch what happens when we square P sub 1. The cross terms cancel beautifully, leaving us with x squared plus 2 plus 1 over x squared equals 9. Subtract 2 from both sides, and we get our second seed. P sub 2 equals 7. Now that we have P sub 1 and P sub 2, we can finally reveal the pattern behind all higher powers. We can now derive the general formula for all the other powers. The trick is simple. Always multiply the previous term, P sub n minus 1, by our starting value, P sub 1. Now look at the multiplication. We take x to the n minus 1 plus 1 over x to the n minus 1 and multiply it by x plus 1 over x. When we expand, we get four terms. The first and last terms are x to the n and 1 over x to the n. That's exactly P sub n. The two middle terms simplify to x to the n minus 2 and 1 over x to the n minus 2, which is P sub n minus 2. So this gives us the core relationship. P sub 1 times P sub n minus 1 equals P sub n plus P sub n minus 2. Now we substitute P sub 1 equals 3 and rearrange to get the climbing rule P sub n equals P sub 1 times P sub n minus 1 minus P sub n minus 2. With P sub 1 equal to 3, our final rule is P sub n equals 3 times P sub n minus 1 minus P sub n minus 2. Let's immediately test our formula on the first real challenge. The odd power, n, equals 3. We substitute our seeds. P sub 3 equals 3 times P sub 2 minus P sub 1. That's 3 times 7 minus 3. P sub 3 equals 18. The formula works beautifully on the odd exponent, computed using nothing but basic arithmetic. Instead of calculating every single power one by one, we can climb much faster by organizing everything in a simple table. Here you can see P sub 3, P sub 4, P sub 5, and P sub 6. Let's jump straight to our odd power P sub 7. Using the values from the table, P sub 7 equals 3 times P sub 6 minus P sub 5. That's 3 times 322 minus 123. P sub 7 equals 843. We handled large, even, and challenging odd exponents without ever solving for x and without touching a calculator. Using the simple arithmetic recurrence relation, P sub n equals 3P sub n minus 1 minus P sub n minus 2. We went from x plus 1 over x equals 3 all the way to x to the 7th plus 1 over x to the 7th equals 843, using nothing but the previous two numbers. This is the power of finding the pattern. And if we wanted the answer to the impossible question from the start, x to the 99 plus 1 over x to the 99, we would simply continue this chain 92 more times. The final answer would be a huge integer, but it would come entirely from repeated multiplication and subtraction, not from solving a 99th degree equation.